Yeah, good morning, good afternoon, good evening, everybody, and welcome to Wednesday, EMinar Day. And it gives me great pleasure to have Maxim Smirnov talking today. I've been trying to get Maxim to talk for the last couple of years and finally got him nailed down to today, talking to us about the DREX project. But before I introduce Maxim, just a quick reminder, we're running towards the end of the EMinar, so if you want to see the prior ones, just go on the MTNet EMinar page. And then you can see the YouTube links and the presentations of prior EMinars. We have two more left. There's one next week, and we don't currently have a speaker. Unfortunately, Michael Faraday isn't available. So if any of you want to speak, please raise your hand and talk about anything you like. All research is good. And then in 2 weeks' time, we have an open mic. And I asked ChatGPT what collective noun is for magnetotellurics specialists, and ChatGPT told me it's a flux. So here's a picture of a flux of MT specialists from 1978 in Murnau in Germany at an EM induction workshop. So we're going to have an open mic up to 2 hours on any and all aspects. So please send in any questions you might have that issues that you want to address in 2 weeks' time. But today we have Maxim Smirnov, Deposit to Regional Scale Exploration, the DREX project. And Maxim has got a fabulous CV. His research focused on development application of EM methods in geophysics, particularly in the MT method. Done a lot on processing, and I've used his processing code in the past very effectively. And 3D modeling of MT and other EM data. He's made a number of contributions to the structure of Fennoscandian lithosphere using EM. And during the last years, he was leading several field campaigns, acquiring long period data, including first measurements in the Svalbard. And he's also leading a task within the EU-funded project related to archiving MT data. So I'll stop share there, Maxim, and invite you to share your presentation.
Okay, thank you, Alan. And then I start sharing. I guess you see my proper screen, right?
Yes, looks good.
Okay, and okay, Alan, thanks for introduction. And I must say that this initiative is very great. That this EMinars are organized, and that creates quite a good educational resources and information resources. And of course, thank you for letting me finally talk, even though I was perhaps postponing to get more done in the project, but that's as usual. Everything stayed preliminary, and we just need to go on. Anyway, so this talk is the joint efforts of several researchers who are working together within this project. And you see the names who contributed directly to the presentation with the slides and the work done. And as I mentioned also, all DREX working group are very much appreciated for their contribution, and many participated, or most of them, they participated in collecting the new MT data and preparing various, doing various processing and modeling. So that's the contribution what we have. So a little bit about the DREX project. So DREX project was funded with an RMN2 joint call, which is was organized under Horizon 2020 program, and the consortium we formed includes the Louisville University, GTECO, Institute of Geophysics of Czech Academy of Sciences, Earth Science Institute, Slovak Academy of Sciences, and two big mining companies operating in Fennoscandians, LKB and Boliden. So they're located physically in the main offices in Sweden, and Boliden operates in Finland and and Sweden and other places. LKB, it's one of the largest producers of iron in the world and in Europe. So, and at the later stage of the project, Norwegian Geological Survey also joined the project. So, just a brief summary. So I will talk about a bit more about the DIREX project, the concept, and about the Finascandia, a little bit of a geology. Then, in fact, because of magnetotellurics is, let's say, the main geophysical method what we use to characterize mineral system. Again, I will say a few words about this. So that's I will say a few words about the history of magnetotellurics and Finascandia and what the data available, and then of course focus on the regional and deposit scale MT surveys and what we collected, and some details about the data processing and inversion. So, and then of course finally I will show preliminary magnetotelluric models together with potential fields and some glimpse on the first joint inversions what we started. Again, the project is let's say in the second half of its duration, but around 1 year left. So it's like the final joint inversions that's coming, let's say, in the next year, and perhaps we'll have some other opportunity to present more detailed information or results from the DIREX project. So DIREX project, again, as I said, is funded as a joint call, EMinar joint call under Horizon 2020 umbrella, and the basic concept is focused on mineral system, and as one of the important components, it's of course unification, integration, and of various geophysical data in order to describe how the deposits was formed. And the DIREX builds on paradigm, and on this paradigm research is exemplified with magnetotelluric data combined with other geophysics. And the prospecting areas what we selected, they are in on obvious reasons in Sweden, Finland, and Norway. And the Norway, in fact, came at the later stage of the project, so that's some changes occurred, and in fact originally it was planned in Greenland, but for various reasons we had to move to Norway, which I think that in fact turned out to be rather positive development for the project. So in brief, the main objectives of the DIREX project can be formulated that the first one is we're building on mineral system paradigm and collect new magnetotelluric data and combine with available regional data, gravity and magnetics, of course, in the 3 prospective areas in Sweden, Norway, and Finland. And currently almost all surveys are done, and in Sweden and Finland we're getting closer to the final result. So it's still preliminary until it's published, but I will show what's the current status, and then probably it won't change very much. In Norway, that's just in the process, so there will be no much discussion about Norwegian data except the data themselves. And then, of course, the second objective in integration of all available data at regional and the deposit scale, and then in the end, building the common Earth model, at least at the deposit scale, or integrated Earth model at the regional scale, and integrating all the available geological and geophysical information. So mineral system concept, I would refer to excellent EMinars, which has been presented earlier. Graham Hansen, Graham Beck, Phil Wanamaker, and in some other presentations, EMinars, there was very detailed explanation of the mineral system concept and some references. But as such, mineral deposit a small part of large and often deep geological content as mineral system. And that can be sort of exemplified in this diagram where we have an energy source, fluid flow source of metals, and then depositional mechanism and fluid outflow where this elements are concentrated into the mineral deposits. So about the geological setting, so we're in Fennoscandia, and it's a Precambrian area, and consists of various domains, and here depicted with red areas is Archean rocks at the surface, and Proterozoic, the rest of the Proterozoic part, and the green one is the Caledonian orogenic rock. So the main, let's say, one of the main boundaries, Rache-Ladega shear complex, so which subdivides basically Archean and the Proterozoic part, even though most of the rocks on top here are Proterozoic, but it's believed that the crust is still Archean, at least until this boundary. So some more details can be seen on this picture, and then in fact it's compared to the previously derived conductance map, and I will say a few words about it on the coming slides. So focusing on the Swedish part, and then I will perhaps say a little more words about our area in Sweden. So, and we'll show a little more examples. So that's the formation of this area, and that's the most tectonic events happened in Svikafenian during Svikafenian orogeny, which included several accretional events and at least one or two subduction events. The main one, it's around 1.89 billion years, and the later one is not really clear, so that's still debatable. And the Gällivare area, where we have our the regional scale measurements, that's situated in back arc settings, and two major ore forming events with largely hydrothermal activities occurred during formation of the arc and the back arc. At the early stage, that's when the volcanic massive sulfides and iron or apatite were formed, and then the second hydrothermal event, and during last accretionary phase, that's the later one when IOCG and orogenic gold deposits were formed. So there's a two distinct time when these deposits were formed, and a picture basically of subduction for this area. So I will get back to this when we will talk about the magnetotelluric model, but a little bit of historical overview, in fact, what we have in Fennoscandia with respect to magnetotelluric data. And in fact, the activity in Fennoscandia started rather early. In fact, the first measurements were already late 70s, and mostly most of the data were, let's say, in the early stage collected as induction studies, and the few references. And I can point that, for example, this green array, that's carry point power, collected magnetovariational arrays. Then later on, Svekolapka array was collected, and Polar and Torkild Rasmussen did some work along the phenolora profile, and some empty measurements were collected around the Sealand impact crater, and then quite a few data in Denmark. But most of the data, in fact, are not saved as in a digital form. So that's sort of more like a historical data, except, of course, the Svekalapko and the Sveka profile. And the later, what we call the BEAR project, that's started in 1997. And the array covering the entire Finlandskandia with relatively long period recordings, about 2 months. So 49 sites measured, and in fact, it's resulted in creation of the conductance map for entire Finlandskandia, basically conductance map for entire crust, and the normal model for the deeper lithosphere. And that combines all the previous magnetotelluric data. In fact, the BEAR data were also used, but not actual 3D inversion by that time. But a lot of, let's say, interpolation and geological, in fact, information was used in order to derive this conductance maps. And you can see the major, let's say, the structures, which are, for example, related to Archean Proterozoic boundary, and that's about where our prospecting areas are located. And then, of course, the Caledonides. And then the later stage, that's basically almost up to now. And in fact, DREX area is included here, but they're not marked on this map. So that's the next map comes. It's listed, I list only those, let's say, published surveys, which you can see on the map, but there are in fact more empty data collected, and especially commercial, industrial data, which some of them I'm aware, but I don't have, for most of them, I don't have even information about the location. So that's perhaps that's the next stage to collect all of the magnetotelluric data in Finlandskandia. So switching now to DREX regional magnetotelluric measurements. So that's now the map of collected sites. So that's in Sweden, the regional magnetotelluric service centered around Gällivare, with 2 large mining activities. That's mine-buried iron ore and the former copper deposit, well, which was mined long ago, and now in prospecting, and the Pyhäsalmi mining area, and Røros in Norway. So in a sense, similar geological settings, but it's also, there are quite some differences. So that's what we will perhaps see later on. So I will talk mostly about these 2 areas, still focusing on the Swedish side, and then show the data what so far been collected around Røros. So about the data collection, so the field campaign started 2021, and in fact some of the data will be added in the gaps and filling in so lost sites or bad sites. So it still will be, some activity will continue this summer, but most of the data were collected during the summer field works, but some were added also during the winter. You see some activities in Sweden, Finland, and Norway. So the typical recordings, data recorded were for 2 days, continuous recordings with sampling 128 Hz, and simultaneously burst recordings at 4 kHz for about, actually for exactly 2 hours starting midnight. So first of all, that allows to synchronize all the measurements, and for example, data in Finland and Sweden, they were collected at the same time, so they in fact were used even for remote reference. So that's one of the advantages. And another thing is during the night, anthropogenic or cultural noise is lower, is stronger. Signal at night, so signal to noise ratio we expected stronger. So all the data were processed with robust remote reference processing, and as I mentioned, we used the remote reference, and then in fact also mutual remote reference. So all the sites recorded at the same time, and in fact about 10 instruments were used in, for example, in Sweden, and 10 in Finland almost simultaneously. So there were plenty of sites recorded in fact at the same time. So again, some things didn't work exactly at the same time, but a lot of overlaps. So all the remote referenced sites were assembled and to derive, let's say, the final estimates. And of course, the power harmonics were filtered before estimating the transfer function, and then some coherence thresholding was used. And that's one of the examples of transfer functions, the main component impedance. And you can see in the gray several remote reference estimate for one particular site, and this blue, it's finally assembled, basically average, robustly average, so all the available remote reference sites. And something that what we tried also in Sweden is to use the remote reference electric fields as well from the remote reference sites together with magnetic fields. And that's the comparison. To I must say that this particular remote reference was located in about 60-70 kilometers from the measuring area, and that was relatively quiet, I would say. So electric fields were in fact quite a good quality. And you see just a 3 example again, apparent resistivities of main impedance components, and blue in fact that's the remote reference for electric fields. Well, the problems at high frequencies, they remain problems, but it's still quite comparable, and that's so let's say good side, no difference. And then you can see filter little glitches of 16 hertz. That's the main frequency for train system in Finland, in Sweden, and 50 hertz filter rate. So that's was quite successful to use also electric field for as a remote reference. So I showed for high frequency recording, for in fact for a longer period, it was pretty much similar behavior. So now switching to basically all the sites. So that's just to show the complete set of 399 empty sites which were used in original empty DRX empty survey in Sweden. So that's pretty consistent estimates. You can see general behavior. So there's plenty of so I plotted main impedance components in the same quadrant now, and you can see that plenty of sites have phase out of quadrant, indicating quite a strong 3D effects. Nevertheless, those data, in fact, we were able to fit quite well. So, and so the next is the Finnish side. Again, quite consistent estimate, a little bit more noise at the highest frequencies, and again, rather consistent estimate on the transfer function. So that's the again main impedance components, appearance resistivities, and phase. And here I plotted in minus I omega t convention, so that's the opposite. Still about a similar behavior, rather consistent, and then plenty of sites with face out of quadrant. A bit more homogeneous coverage of the area with a little easier access than in Sweden, and then you can see that there are a number of areas which sort of have no roads, and in fact, like for example, some of the areas, they are national parks, which requires a special permit, and of course, some difficulties to access, even in the winter time. That's the, and in the end, coming to Norway, so that's the currently collected data. So few will be added this summer to fill in the gaps. So that's again similar to Finland, rather homogeneous coverage. More or less consistent data with some outliers that's perhaps will be sorted out this summer. A few things which are not fixed with the face, but again, quite a few sites with the face out of quadrant, and the, let's say, the processing or sorting out the data here still on the way. Showing the face tensor plots for all the three surveys. So you can see again the data are rather consistent. So starting from let's say high frequency short periods, going to the longer periods, gets a little more conductive, and then again going towards a little more resistive with the depths. So, and a very consistent trend, which is basically pretty much coincide with the direction of the main structural, this Reicheladiger zone, the direction. So in a sense, similar behavior in Sweden. So some conductive stuff at the surface, still conductive at the mid-range, and getting a little more resistive, and very consistent, in fact, direction. Again, it's pretty much aligned with this main direction of the structures and the longer periods. It's sort of indication of rather good data quality, and for the most of the data, with some little exceptions. So similar behavior in Norway, and it should be noted that the coastline is about 50 kilometers from the survey, and in fact, in another direction, we'll have a Caledonian front, and in fact, this direction again very much consistent with the perpendicular to Caledonian front, in a sense, also to the coastline with rather conductive sediments. So the total conductance in ocean is rather high, so from the previous modeling. So a few words about the deposit scale, and that's what I was trying to indicate. That's the already in Gällivare, so now it's in Sweden, and that's around active mine. So that's Malmberget LKB iron ore mine. So that's the city itself. So the deposit scale, that's not all sites, but let's say collected 1 year earlier, before the start of the DREX. And here I indicated the quality of the transfer function. So the green one says the good to excellent data quality, yellow good to acceptable, orange acceptable, and red one, they were just excluded. So that's due to basically some noise or whatever problems, in fact, with the site. So what I wanted to emphasize here is that, in fact, even measuring the data in relatively active areas still allows to derive data which can be used to derive or to use for, ultimately for 3D inversion and to constrain the final conductivity models. And what I classified as green good to excellent. So that's an example of the good and excellent data. And then, for example, orange, those sort of dubious data have some very sharp and perhaps non-physical behavior. So that's, but still some part of the frequency band can be used for, let's say, inversion. So those were indicated as classified as orange sites. Something that was, let's say, part of the planned activities within the DREX is application of multivariate analysis in order to estimate the transfer function. And in fact, we built this sort of development on top of our previously developed object-oriented MATLAB framework. What we did with Gary Egbert, and again, I would refer to EMinar given by Gary Egbert with some explanations also given for multivariate analysis. So in brief, so we decomposed observed data, and the data here refers to the already transformed to frequency domain. So that's for one particular frequency, and all the components assembled in data matrix with all the segments. And then this data matrix is decomposed to spatial and temporal modes. So A stands for temporal modes, polarization parameters, and U is the spatial modes. And that's just, in fact, the example, for example, is the same area, but for the previous mask array, together with image observatories. So that's the continuously acquired image observatories, even though still having sometimes some gaps. And then magnetotelluric data, so that's the long period data. And eigenspectral value is shown with as often two dominating first main principal components. And again, so that's one of the activities which we undertook in within the project, that's to transform this MATLAB framework to basically Python package. So in a sense, it's a direct translation, but with some rearrangement of the classes and perhaps later integration with new development going on in Iris with Aurora package developed. So that's there are a few things which are still not finished, but being, let's say, work in progress quite often. So that's an effect example of the first 6 modes, what has been derived for this specific period of around 200 seconds. And you can see, in fact, the first 2 modes, they are very closely resemble the first principle plane wave source, and then as a component, they are very closely related to this curl-free gradient modes. So again, some details can be read or seen in Gary's presentation, so I won't, let's say, focus on this, but using this, let's say, first mostly plane wave modes, let's say, so we can derive the transfer function, and of course idea is to estimate sort of more plane wave impedances, and again we are situated in a high latitude where we can expect in principle some source field effect, and here you can see the comparison of multivariate with our sort of this multi-site, multi-remote reference robust estimate, which are given in red, and the blue is multivariate estimate. So there is some differences in some period ranges, and it's sort of a little difficult to say which one better and which one is worse. So that's one side, that's another side. So there's quite a lot of similarity. So there is a little bit perhaps better for, in some cases, for multivariate case. But in principle, they're relatively similar. So again, that's just to support the conclusion what has been done, in fact, earlier, that let's say up to at least 1000 seconds were relatively safe with respect to the source field effect on impedances. And then another way to look, in fact, to the source field. So that's taking all the spatial modes estimated. They in fact can be remixed and in fact remixed in randomly. So that's sort of orthogonal projection or orthogonal rotation of the modes. And you can see sometimes the higher mode, they have a more effect, and then of course if they contain the source field effect, so they will be sort of will be visible as a certain bias in impedances. And then at some periods you can see that there is some events or periods where there is some source field effect which sort of can be expected. But nevertheless, let's say the average is always kind of focused on this sort of mostly plane wave estimate. So that's about the data processing. Then after all this nice and high quality estimated transfer function, of course, the next step is Magnetotellurics 3D inversion. And we mostly used so far ModEM. Thanks for Gary Nazer and Anna for development, and some little modification, or in fact not modification code, but the way we used it. So you can see this standard objective function or penalty function what we minimize with data covariances and the model covariances included with a priori model. And typically we minimize L2 norm, and however, as again was discussed previously on other EMinars, in fact, we can minimize the other norms. And what we tried, in fact, here is to use the L1 norm for residuals, or alternatively, for example, Huber's loss function can be used. But this sort of minimization can be formulated using iteratively related least squares, and it's a relatively simple modification when the weights are basically estimated based on the residuals. And in this case, it's referring to L1 norm, but this one can be replaced with the other constant, and other loss function or penalty function can be minimized. So in this case, the purpose is to deal basically with the outliers, bad data, and perhaps some inconsistency with the modeling. For example, if not enough resolution to, let's say, describe or let's say to model some features in responses, even though they are, let's say, physical themselves, but the discretization, for example, not sufficient to fit the data. So that will be basically ending into this weights. And the way we implement it, so we run the ModEM inversion and then modify basically the, as you can see, we modify the errors, and then the new errors are supplied to the next iteration. And then iteration is referred because of its nonlinear problem, so it's referred to complete solution. So for linear problem, so we have a solution and reweighting it, but with a nonlinear, this iterations are referred to already in between the complete solution. So, and a few, of course, for different areas, we tried different approaches. So we run with the different parameters, different site selection again, different objective function minimized. So with this iteratively reweighted data errors going towards L1 norm. And in all the cases, what I will refer to, it's full tensor was inverted. different error floors were assigned. And again, when we reweighted, for example, we started with rather low error floor, but due to reweighting, it's basically compensated. And for example, the final RMS, and that's in this case, I'm referring to finished data. And with reweighting, of course, there was no problem to reach the final RMS close to 1. That's basically a matter of how many times these iterations are done. And typically it was in fact 2-3 times sufficient to get to RMS 1. And well, the mesh, you can see it's about 100 by 100, 120 by 120 with about 10-15 padding cells. We used the different model covariances, default auto-regression model covariance, even though it was also used the diffusion model covariances, again, slightly different results. Default smoothing, and the typically, in the end at least, we were running in this basically complete period range with not about, but exactly 7 periods per decade. That's the final results, what I will show, at least for Swedish side. So some variations are possible for other areas. Something that I want to show is the effect of this iteratively reweighted errors. And it's always, so that's, let's say, I would say that's a typical example. So that's the first iteration, or just original standard inversion. And then you can see the data indicated with the symbols. So X, Y, and Y, X components, the main impedances, and with the lines, it's predicted responses, transfer functions. And then you can see the data feed, and there are little glitches, for example, in the phase, which were not possible to feed. And then, in fact, after reweighting, you can see that, in fact, in this area, the errors or the weights basically increased the errors. And the effect, and for example, at the especially the last periods, for example, in this specific case, no change in errors. And you can see that, in fact, after reweighting, the feed is a little bit better. So again, the scale is exactly the same. So, and especially at certain periods, and then still those periods sort of ignored, and then the data mostly fitted within the error bars. And that's pretty much typical example, and perhaps we can show it a little more later, but even the phase out of quadrant, in fact, quite often was fitted better. So that's the outcome. And just to show, in fact, what's the differences in the model, again, that's already going to the regional model in Sweden. So there's no scale, but it's about 150 by 150 kilometers. So the depths for this either surfaces is around 20-30 kilometers. So it's mid-crust, and the either surface is 20 meters. And just to compare that, the red ones are original, basically the first iteration, and then the blue after few reweighting. There are changes in the model, obviously, but let's say the main features, of course, are preserved. The data fit is better, even though the model slightly changed. So that's the outcome, and that, of course, can be discussed. So switching to, in fact, a little bit of an interpretation and the results what we've got. And again, I will talk mostly about magnetotelluric data and a little bit of potential field data. So first focusing on in Sweden, and that doesn't cover entire regional scale, but let's say 1/3 of it, but still centered around Malmberget deposit and Nautanen. So Malmberget, it's iron oxide deposit. and it's one of the largest underground iron ore mine in operation. And now then is OCG type deposit. Previously mined, and it's associated with the major Nautanen deformation zone. So it's a crustal scale deformation zone. So what we were working with, so that in fact we have several scales what we can compare with, and that's the previous data which were collected in the previous years. That's within the Moscow project. So that's basically close to continental scale. And then in the yellow, we have our regional survey. And then you can see how this the spacing, in fact, in between sites changing, or the resolution, the sampling, site sampling. So within the Moscow project, we're able to sample the area still with quite a lot of gaps, up to 30 kilometer spacing. And when we switched to DREX, the survey was designed to have the site spacing around 5 kilometers. And yeah, it's 100 by 100 kilometers area. And then we go for more deposit scale. So we have 1 kilometer grid covering, in this case, Nautanen and Malmberget. And then, in fact, we went even smaller scale to get more detailed information, and that's the control source. Relatively deep control source covering the first kilometer, let's say. So that's ultimately those scales what we're working with. I will not show almost anything from here. Well, in fact, one example, but most of the, let's say, models come at these scales, these two scales. So that's the regional scale model in Sweden, and then deposit scales with, let's say, which were ran separately with detailed. So there are several scales what we ran it, and we didn't use in this case as sort of nested approach, but we ran them basically separately for two deposit scale, and then in fact one which was let's say extended scale, which combines both area, and in fact it provides quite an insight into, and provides the new information, let's say, in the structures, which was in fact previously guessed from the geological information. Then we have regional scale data. So here this Magnetotelluric model as the shades for a 50 meter isosurface overlap on the gravity boogie anomaly and magnetic map, and there's plenty of correlation you can immediately observe, but of course there's some areas which are not obviously correlated. So that's at least first indication for let's say potentially very interesting data set for joint inversion. And that's, again, I will show in the end first examples, but that's just the preliminary examples, and certainly not final ones. So focusing a little bit more on the gravity. So that's the again repetition from the previous slide with a little bit more focus on let's say Magnetotelluric data, and that's in fact underlying regional gravity model, but relatively deep. So it's a little bit difficult to compare on this scale, but again, there is quite a lot of let's say the correlation, but no correlation as well. So that's the, something that comes later on the stage, and we hope to get better models. Now I'm just zooming into the more closer to a deposit scale. So when we in fact ran the deposit scales themselves, there was no obvious connection to this let's say big regional structures, even though this intermediate inversion exhibit much better correlation, or there's, let's say, more obvious connection to this deeper conductivity anomalies. And now we're zooming even more. So that's in red one, that's the pieces of the regional scale models. Light green, that's the small deposit scale, and then that's the combined, which again connects to the big model, and then of course the more details coming on the small scale. And for example, in again, so this mine-buried model, which is very well correlates with, of course, the, let's say, known deposit, at least at the surface, that comes exactly where at the moment iron ore is known, and then some expected more iron ore, and some deeper connection to the deeper source of mineralization in Nautanen, which correlates quite well with Nautanen deformation zone. And just an example of what control source, in fact, of course, that's a rather small survey, but it's pretty well also matches magnetotelluric model, which is in this case contains just a few, maybe 6 empty sites in this area, and the still gives better description, of course, obviously at the surface. And then switching to the next slide, that's the combination or let's say comparison of gravity and empty model in Nautanen, and that's the basically single inversion. In green, that's the isosurface of 50 ohm meters from a magnetotelluric model combined for both area a little bit extended, and then the orange is in fact the gravity dense gravity. So I don't remember exactly what's the density isosurface, but it was basically selected in a way that it also correlates a little better with the empty results. And in fact, this deeper source of surface mineralization, that's pretty much very well correlates with the gravity model in this case. And then that's the gravity anomaly at the surface. So that's the gravity data which were used for this area. So switching to the Finnish side. So the survey area is located again in the similar setting as in Archean Proterozoic boundary within Rahi-Ladoga zone, and that's one of the largest VMS deposit in Pyhäsalmi. So there's plenty of metasedimentary rocks metamorphosed, so black shales and thrusted over the Archean. So mostly the rocks on top are Proterozoic with some Archean rocks to the northeast. So going towards the 3D magnetotelluric model, that's the slice through the middle, the depth slice, and you can see the conductivity anomalies, which one of them, in fact, correlates very well with the Pyhäsalmi ore deposit. And you can see this subvertical conductor. And at least it was concluded that the depth resolution for this 3D models, at least the structures, what observed is about 40 kilometers. So going towards the more detailed, so that's isosurface of 10 meter with the coloring which showing the, in fact, the depths. So the blue is about 40 kilometers and the red going to the surface. And again, some of the deposits, you can see they're sort of associated with the conductors, which are sort of disconnected from the main body like Pyhäsalmi. So there is a subvertical conductor, but not directly connected to the main conductor. And then some of them deposits or conductors are quite well associated correlated with the surface conductors, and they're coming sort of to the surface. And the general trend, the main trend, again for this the regional scale, the crustal anomaly, that's the pretty much correlates the main direction of the shear zone or Archean Proterozoic effect boundary. So I perhaps leave interpretation of the conductors themselves for a later stage, but we can speculate that, of course, a lot of graphite is present, and perhaps, at least in Sweden, magnetite can be responsible for crustal conductors. So that's perhaps part of the, let's say, discussion or later more detailed work on interpretation of the models what we've got so far. But a little bit of about the deeper, in fact, lithosphere structure, which I, in fact, did a little bit earlier after we acquired data in Sweden again. The data are coming from Archean Proterozoic boundary, and it was earlier noted that Archean lithosphere seems to be rather conductive and perhaps relatively thin. And what I did is basically averaged all the data and took the determinant of this all averaged in Sweden data and derived this 1D response. So again, this is just amplified part of the crust and then entire lithosphere, and you see it's relatively conductive with these conductors coming around the mid-crust levels, and that's where all the main conductors, which I shown before, that's where they are sort of concentrated. But otherwise, the lithosphere seems to be also relatively conductive. So the same, in fact, happens in Finland. So taking the all average of direct sites ends up in approximately the same behavior. So then the question, of course, whether this crust and lithosphere is Archean or Proterozoic, even though in mostly we can, at least according to all the evidence, that's Archean. And then in fact, so that's the location. And then in fact, as a teaser, that's the result of running 3D inversion for entire Mashka area. And that's a conductance map. That's a little difficult to read, but that's a conductance map in the depth range from 100 to 300 kilometers. And you can see a clear transition from something conductive to more resistive lithosphere. And well, the conclusion basically comes to so that's the results coming from Archean Karelian crater, and that's the similar thing done for data from previous Mashka and Emma measurements, which are sitting on Archean rocks on top. So that's an Karelian crater. Those data, what I showed, perhaps Archean in Narbutum and around Pyhäsalmi, and that's somewhere further down in Sweden, Jämtland or Blue Road profiles, Svikafenian. So the same average, and that's the same 1D with much more resistive lithosphere, Paleoproterozoic lithosphere. So that's something sort of interesting to try to interpret in the later. A few things what we did or started to do with the joint inversion and Jan water. That's very preliminary results. Used GIF3D to invert the gravity MT using motion information constraints. So again, I won't focus on the results. At the moment, it's really preliminary, and that certainly will be updated. But as already previously mentioned, the regional scale data, let's say, excellent for applying this joint inversion, and we expect that will improve the resulting models and the resulting interpretation. Not least to say that we also did some comparison between various, or at the moment, different 3D codes, just to make sure that those features what we derive, they are stable. So in this case, the data were the same, slightly different discretization for ModEM and the VRHI codes. In fact, the discretization was the same, the GIF3D is different, but you can see that in fact most of these conductive features, slightly different popping up, but sort of very similar. Again, that's basically the testing different code, and that's not to let's say select the best code. So it's not actually the benchmarking of the code, but it basically the purpose is to see what's the most important and stable features in the models, in a sense related to sensitivity analysis. And that's basically coming close to the end. A few practical notes. So during onset of the project, we created QGIS project, quite intensively used geoscience analysts to combine all the data and overlap with geological, and perhaps will be moved gradually to Leapfrog. So there is a website, so some of the information can be found. And then we also used, in fact, Nextcloud, our own repository, to exchange all the data. And basically, it's unlimited storage, which in fact helped quite a lot to exchange and well, that's not archiving, it's basically data exchange. Something that I want to bring to your attention as well, it's European Plate Observing System EPOS project, where we have some active part working with archiving magnetotelluric data, transfer function, time series, and in fact conductivity models. Work as usually in progress, but plenty of data, well, some data, let's say. 1,000 or so data points now available as a transfer function, time series still coming, and the electrical conductivity model, basically SMAP, what you have seen. But officially, EPOS portal was released, and in fact, you can find in this link, access the portal and perhaps play around with the portal and try various use cases. And so the idea, of course, that's integration various geophysical data. Perhaps you will find something useful, and of course, in certain point may contribute with, at least from our side, with magnetotelluric data. So conclusions at the moment. So what we did so far, it's mostly focused on magnetotelluric data. So the work with potential field and integration of potential field on a regional scale, and specifically joint inversion is just started. And then, of course, the understanding of the models with respect to tectonic settings and mineral system and deep source of mineralization. It's ongoing. So if during discussion I may kind of shade the light on some of the hypotheses what we so far have, but otherwise still a way to go. And we hope that that brings, let's say, more insight and more interesting development. And of course, again, thanks to all contributions during the project. So nice and sometimes challenging field works, but in the end, I think quite good results, at least with respect to magnetotelluric data. We're getting rather robust and stable models. So I will stop here. So thanks for attention, and I guess that's time for some questions and some discussion regarding, and of course comments from those from our consortium and co-authors who wants to say some more comments on some questions are welcome. Yeah, thank you.
Well, thank you very much, Maxime. Absolutely fabulous. The data sets, you know, I got a PhD with 13 MT sites, of which I only did 1D models of 6. We've come,
yeah, exactly. So that's a different scale.
Yeah.
So, no,
absolutely fabulous. I've got a few questions, but I'll let some questions roll in from the audience first. And those of you, if you wish to speak, please raise your hand and I will make you speakable. Otherwise, send a question in your Q&A. So we have one question already that's been there for quite a while now from Leo Fox about the slide on remote referencing comparing E and H. Why is the longest period 10 seconds when the measured flow is 1,000 seconds?
In fact, it's just an example. So an example that just turned out to be that I have first found 4 kilohertz sampling for this 2 hours comparison of electric and magnetic as a remote reference. And that's, as soon as you know this regional scale, that's the most important information. That's where it comes from. So that's what I showed. But I already mentioned that for the longer period and the longer periods, we could get up to 1,000 seconds. That was a similar conclusion. So again, that's perhaps a little bit deficiency of this example. I could have added a longer period.
Yeah, I've had good success with using the electric field in the AMT deadband to get superior estimates.
Yeah,
because the noise in the AMT deadband is in the magnetic field. So the using the remote E has been very successful.
Yeah, well, that's at least turned out, at least here, you can see that it didn't improve much in our case. But that's the already local problem for electric fields, at least. So that's the...
Can I ask you whether you had an opportunity to look at how correlative the audio magnetotelluric signals are? Because I did a study about 25 years ago now, where I had a station close to Ottawa and I had one 25 kilometers away and one 50 kilometers away. And the one 50 kilometers away, the measurements at AMT frequencies, particularly around the deadband, didn't correlate well enough with the local site. So I've always had as a rule of thumb 25 kilometers for the remote reference distance for AMT frequencies.
Interesting, because of AMT ranges, the main source is equatorial thunderstorm activity, which is a relatively global source. So we would in general expect much longer correlation, let's say distances. And honestly, I mean, that's basically example with a remote reference, which is situated about 50, 60 kilometers, 100 kilometers from this site. And usually I didn't observe any, let's say, specific problems. But again, and then we start also to mix with local mutual remote reference. So when we have a set of sites installed in, let's say, smaller array, and then they are sort of supporting each other's remote reference. So I don't have, let's say, systematic answer, so which is better. But as I said, remote reference, which is like 100 kilometers away in a quiet place, certainly works for, and that's an example for, in AMT band.
Oh, great. Yeah, we have a question from Doug Oldenburg that's actually in the chat, not in the Q&A. Thanks for a great talk. I may have missed it, but were you handling your outer quadrant phase data through the weighted L1 norm on Data Misfit?
Yes, and I must say that I should have, again, it's this examples were varying from presentation to presentation, and then I couldn't in the end find what I wanted to show, but I said that, in fact, phase out of quadrant was fit during the inversion. And the main thing that when, let's say, it's mostly fit during the first run, the first iteration, then they were not downweighted at all. And then, in fact, what happened, it was quite interesting example that one side was phase out of quadrant was, let's say, fit so-so. And then after reweighting, the fit was even better. But one particular side was phase out of quadrant. And it seems like inversion in principle, because of like discretization, the model itself allows to reproduce this phase out of quadrant. But as soon as we downweighted the sides, let's say around, which may be affected by noise and have some specific data points which cannot be fit simply, then downweighting those provides better opportunity to fit those physical behavior, in fact, including phase out of quadrant.
Yeah, the one interesting aspect is the galvanic distortion, and you know, that can produce huge phases out of quadrant. But ModEM and Verichai's code don't implicitly invert for the 2x2 distortion matrix, whereas at GIF 3D, Max's code, which is, you know, a shell around Anna Avdiva's inversion code, that does. So did you find that some of these things could be explained by local galvanic distortion?
Yeah, I didn't look at, let's say, in such a details, but at least what I have found that, of course, first of all, we have a very thin layers at the surface. So for the deposit scale, we start like with 10-meter layers, and then of course on regional scale there were like 50 meters, the first layers. So they already able to accommodate this galvanic distortion. So you see that the first few layers, which are relatively thin and not useful, I mean, it's they have nothing except the galvanic, let's say, effect. They pretty much reproduce this galvanic distortion and allow to fit the data. So just basically ignoring those, that's already, as I said, enough to fit the data. Well, I'm talking about the final model. But of course, that's what I also was referring to, the reason for the weighting. So if the cells are too big and there are sites which are sort of located, maybe sometimes even two sites in one cell, that happened also, then there is absolutely no way to reproduce this galvanic effects. Yes, and those will be downweighted. That's for sure. That's what happens.
Yeah, Doug has raised his hand, so I think I've made you able to speak, Doug.
Oh, can you hear me?
Yes.
Oh,
Yes.
okay. Yes, I'm still a little bit confused. So you downweight these data that are out of quadrant, but then when you actually go ahead and do a forward simulation, are you able to produce data that are out of quadrant, or are you still limited by the plus minus 90 degrees?
So what I said is that, in fact, if in the original inversion, the first iteration, you are able to reproduce, let's say, those phase out of quadrant data, then they will not be downweighted. So it's not related to whether it's a phase out of quadrant or not. So it's mostly related to whether the first run of the inversion, the first iteration, is able to reproduce anything from this data. Then they will not be downweighted. Or, well, if they are fitted, then residuals perhaps are small enough so that there is no need to, you know, to downweight them. And what happened that sometimes those data, they fitted even better after reweighting because of some sites around will be, penalized for, let's say, a little strange behavior. And then those, let's say, extreme sites with face out of quadrant will be fitted better. So in fact, I have even an example of that.
Okay, so that's interesting because although we haven't looked at it in complete depth, we don't seem to have found cases where our codes would actually forward simulate responses that were out of quadrant. So that's always been a bit of a mystery. And there's been various suggestions about galvanic distortion and anisotropy that would mean that something else has to be added to our generic models. So Alan asked you about galvanic distortion, but is your algorithm then just able to produce data that are out of quadrant?
Yes. Well, first of all, we're using ModEM in this case, at least. Okay. So that's the ModEM inversion. And it's certainly able to reproduce the face out of quadrant.
Okay, thank you.
That's the way it works. And then, that's extra weights. As I said, they don't remove anything what has been already sort of relatively well fitted. That remains unmodified.
Okay, well, thank you very much.
Yeah, it's interesting, the phase out quadrant business, because I'm looking at more and more mining data these days, and I'm seeing more and more and more data that with phases going out of quadrant. And I don't mean just by 10 degrees, I mean by, almost 180 degrees. And I can't model it with isotropic 3D forward codes or inversion codes. And so I do think that it's probably an expression of anisotropy. And there was a wonderful paper by 2004, was it? The Jaume Paus talking about anisotropy, and that was in the 2D where he had two anisotropic layers at different angles from each other, and he got phases going out of quadrant. So I'm really interested that you can get this in ModEM.
Yeah, absolutely. In fact, I wonder. I have quite a few examples for that. In fact, so I should have shown. But okay, well, I may find it right away, but I can. The only thing I can say that it fits, so it's possible to reproduce the face out of quadrant, and not only one. Let's say so. That's those sites what I have shown. There's plenty of face out of quadrant sites which are reproduced. Some of them are not as well. So as I said, we are limited in resolution, and of course, if site is located in such way that there is no way to get this, sharp boundaries close to it, with just discretization is model discretization is that way, then it may not be fitted.
Yeah, can you just go forward 2 slides to your L2 L1 comparison? That one,
yes.
Yeah. Because looking at that, if you look at the apparent resistivity on the left, there's something like 8 points there that are systematically misfit.
Yes.
That gap around sort of 100 hertz to 1 hertz.
Okay, here, yes.
Yeah, and what you're doing is increasing the error bars so that they fit. Well, I would say that there's some model feature that's not being fit.
So you are saying that it's not fit?
Yeah, it's always a quandary, isn't it? When you have outliers, are those outliers real data outliers, or are those outliers due to Earth structure that we're not modeling? And I would say in your case, seeing as you've got 8 data points, all above those lines, you shouldn't have changed those error bars. If anything, you should have made them smaller and forced the modeling to try and fit those data points.
Yeah. However, it turned out to be because, this period, coincide with a little bit of this strange behavior for the face, these blobs. So what happened is that compared to other site feeds, so of course that's relatively to all other sites data feeds, so they were not fitted as good and they were a little bit downweighted, but at least apparent resistivity ended up with a little bit better fit than here. And even though as you said, you should reduce the errors, but in fact, increasing the errors, it's allowed for better fit altogether. That's what turned out. But again, I think that needs to be looked upon in a complex together with other sites around as well. So because there is an effect. It's not only this one particular site. It's not sort of 1D inversion. So there is a little bit more complex behavior in this case. So we don't know also, well, I mean, that needs to be a little bit more carefully analyzed how the other sites around were affected as well. But I believe that looks better fitted, at least for the blue curve, a little bit.
Yeah, well, if you increase your error bars, eventually you'll find a model that fits, right?
Well, but I mean, you are fitting within the error bars, of course. But I mean, the thing is that it's really going through the circles now. So the data much is better.
Yeah. So we have a couple of questions. I'll jump to Leo's first because it's apropos what we were just discussing. Michel Chateau dubbed it PROC, phase rollout to quadrant. And it's very common in mining data, seen as early as 1991-93 in the ENCODE Trillabel survey. So the 3D codes need to be able to deal with this to reflect the reality of MT in data mining camps, in the mining camps. And I agree totally with you there, Leo. There are some people that are working on anisotropic 3D codes, but of course, instead of going from 1 parameter per cell, you're suddenly going to 6. And that means you're going to have to introduce lots more regularization, and it's difficult enough doing MT with fitting 1 parameter on. Yeah, it's going to be a real rat's nest trying to fit anisotropy unless you can guide it somehow with known geology.
Yeah, but it turns out that there is no really need for anisotropy in order to produce this sort of behavior.
Mehdi Mohammed Vishay says, many thanks for the presentation, fantastic result. What is the inverted resistivity for magnetite ore deposits in the model you showed? As I realized, the surrounding units are more conductive. Which units are they?
Surrounding units, of course, are much more resistive. That's basically the host rock, which is very resistive. So it's gneiss, which is like 10,000 meters or so, and magnetite itself is conductive, but we don't see, let's say, this very detailed ore itself, I mean, ore structure. So it's still a little bit blurred as usual. And the isosurface, what I showed, it was around 5,100 meters. So there's no, that's one of the, yeah, that's the 100 meters. That's perhaps more detail. So that's the conductive thing. So that's everything is conductive. So that's conductive isosurface.
Yeah, perhaps just a final comment, because the questions have dried up, that when you show those 1D inversions, you're not getting the true resistivity of the uppermost lithosphere because it's shielded by the conducting lower crust and the conducting asthenosphere. So those are minimum values.
Yeah, that's right.
Yeah.
Yes, yeah. Of course. Yes, yes. But what I wanted is just to contrast to, you know, proper Zwickau-Fehny lithosphere. So there is some conductive crust, but let's say the lithosphere still, and that's 1D inversion without any a priori M0 or anything. So that's just a data 1D inversion. And it's quite often, in fact, it's yeah, it's able to resolve a little bit more resistive if it's resistive. But yeah, that's right. Yes, that's true. It's relatively conductive in the mid, perhaps not fully resolved. Yeah, that's right.
Well, no more questions. So thanks very much.
Actually, Alan, can I just bring in here?
Sorry, Lindsay. Yeah.
Just one tangentially. And that is, you know, with respect to, I think, Leo's comment about seeing lots of data for the mining companies being phased out of quadrant. Are there, you know, sort of links to that information?
I don't know. I wouldn't know that, Doug. I think if some of the data is publicly available. I think Trilobel is, because that's the one that was worked on by Maria Marchal in the early 90s. But of course, a lot of it is confidential, right? And it can't be talked about.
Yeah, the same in Finascandia. There's quite a lot of commercial data, which is, let's say, I'm aware of, but I've never even seen them. So that's the.
Okay, thanks.
Yeah, thanks, Doug. So I had a client today who told me that he wanted me to produce geologically reasonable models. So I said, well, that's going to be tough, because these most of these codes produce blocks, right? And mining environments are not blocks, so we need to move on a bit from blocks.
Alan, just a quick note, I just let Leo in. He raised his hand with some comments here too.
Okay. Hey, Leo.
Yeah, hi, gents. I'm on vacation, but this is very stimulating. Yeah, Doug, I can send you a few links, but as numerous people have pointed out, most of that mining data is confidential. I'll send you links to what I have, and one of the interesting examples is about 10 years old, from VMS mining camp in Flin Flon. So that was published at that La Lore symposium in late 2014. The second part, I just sent not a question, but a comment to Alan, and I said, I agree with Alan. The MT inversion needs to work cooperatively. I'm just reading what I said, with the locally knowledgeable geologists to restrict models to those which are reasonable geologically. And this is not new. The more complex the environment, for example, the mountain front in Bolivia years ago, I remember Geosystem, I believe Geosystem did MT there, and it's a fairly complicated thrust environment, but they didn't really get what I would call models which were useful to the oil company there, or the oil and gas company, whoever that was, until they sat down and worked iteratively with locally knowledgeable geologists to restrict the models to those which were reasonable. And when they did that, when they put in this kind of a priori information, then they could get useful models. Because as Alan pointed out, if you have to account for anisotropy, suddenly you're going from 2 dimensions to 6, and it starts to become maybe an impossible way to deal with it. If you strictly look at the parameters, you need to add a priori knowledge, I guess is what I'm saying.
Yeah, thanks, Leo. Okay, I think we're kind of wound down. So many thanks again, Maxim. Absolutely wonderful presentation. And the recording will be up live on YouTube channel within a couple of hours. And if you could send me your talk as a PDF, Maxim, I'll make that available on the MTNet webpage.
Yes, I will.
Great. And we're still looking for someone to talk next week. And what I see, Doug's still online. Doug, are you there? How about giving another talk?
No, mine. My first one, I thought the time limit was an hour and a half, and I think I did that. So it's kind of like 2 talks.
Yeah, well, you still hold the record, Doug, for the talking time. It's more like 3. But yeah, but it's still the most viewed EMinar of any by a huge amount, Doug. People are really watching that many times. Okay, thanks everybody, and hopefully see you next week if we get a speaker. Thanks, Maxim. Bye for now.
Yeah. Bye.